This lesson is about the connection between energy and change. So if you want to make a change, you need energy flow. So if I want to change your position, startle you, get your attention, all right, I need to use energy, sound energy, to make that change. That sound energy comes from the chemical energy of my lunch that I ate earlier. Right? My muscles use that chemical energy, convert it into kinetic energy so I can move my arms, to make sound energy, to get your attention, all right, to cause a change, cause you to move. Good example of energy, right, is in the kitchen when you have a hot stove. Put, I don't know if you can see, the stove is red hot, right, so you can see that it is a source of heat. Put my hand over there, I can feel it. I could put water on there to heat it up. Right, that has a high temperature. That is my source. So we identify a source as an area of high energy. So maybe it's hot. Maybe it just has lots of energy in that area. That is called the source. So in this particular case, the hot stove is my source. And energy will always flow from a source to a sink. A sink is going to be a lower energy spot, a cooler area. So if I go ahead and touch that stove, which I don't want to do, all right, burn myself, the energy is going from the source, the stove, to my cooler hand, the sink. I put the water on there, right, the pot, right, those are sinks that are going to absorb the energy from the source. Now that exchange between source and sink occurs simultaneously. Simultaneously means at the same time. So the stove loses the energy at the same time that my hand gains it. Those are two occur simultaneously. And the boundary between those two is called an interface. So when my hand touches the stove and I get burnt, right, when my hand is touching the stove, that is the interface, the contact point between those two, between the hot energy source of the stove and the sink of my cooler hand. Right now, if I'm boiling or starting to heat this water, right, the interface is the bottom of the pan, the boundary between the hot stove and the cold water. And one last good analogy for source and sink is in the kitchen. Right? If I need water, I need a water source. I walk over to the faucet. The faucet is my energy source. Right? That's where the water is coming from. It's going down into the sink. So just like with temperature, it goes from source to sink. Here the water is going from the faucet into the sink. It's winter time. Somebody needs to warm their house. You have a furnace, you have a wood stove, a pellet stove. That's going to be your energy source, and that energy is going to come from the furnace or the stove, and it's going to go to the cool air and warm up your house. The air is the sink, your house is the sink, and the furnace is the source. Good. So, we've already talked about energy source, right, and how energy flows, and how energy can create a change. We already talked about vocab words like source. The source is where there's high energy, like a hot place if you're talking about heat energy. Like on a day like today, think back, you're watching this, it's September, so think back a month ago, summertime. Right? Today's August 21st. Right? It's a hot, humid day. Right? We're going to talk about source. We're also going to talk about sink. All right, we're reviewing that vocab term that you learned about. Right? A place of low energy, all right, like a cool spot. So source and sink. And of course, in between them is the boundary or the interface. So next, let's try an example. Cold Pepsi can. Right, pulled it out of the fridge. Sitting on the table. Right, hot summer day. Right, so hot that there's condensation on the side of the can. I don't know if you can see that. If you zoom in, you can see the condensation water droplets, especially where I touch. You can see the water on the outside of the can. So the question is, where's that water coming from? Right? There's an energy change happening with this cold soda. Right? So first, right, what is the source? Right? The source is this humidity, hot, humid day. Right? The hot temperatures, the hot, humid, the water vapor in the air. Right? the source, we're looking for the cool spot. Well, the cool spot is the soda, right? The soda was in the fridge, right? And the condensation, you can see all that on that napkin, right, is along the surface of the can. The surface of the can is the interface, the boundary between the cold soda and the warm, humid air. Warm, humid air source, cold soda sink, can surface is the interface. So change is caused by energy flow. Energy flows from source to sink. Can we predict that change? Is it predictable? Sometimes yes, sometimes no. It totally depends on the scope and the direction that future changes will take, whether we can predict. General events are fairly predictable. Look at the moon phases. You watch over the course of a month, you can see the moon appear to change phase. You watch the next month, you see the same changes. After watching a few months in a row, you can say, hey, I think I know what's going to happen. I can predict what phase is going to come next. Moon phases are generally predictable, month after month. High and low tide, for those people that live near the ocean. Look at this picture. Beach in Costa Rica. We went there for a summer vacation a couple years ago. Here's the beach at low tide. You can see the kayak, the log off to the left. You can see a lot of black sand from the volcanic rock of the island. Or not the island, the area. Look at the same beach at high tide. Still see the kayak and the log to the left, but now half of that sand is covered. Right, the water is higher. The tides are predictable. Right? They occur high tide, low tide, low tide, generally over a little bit more than a 24-hour period. Sunrise, sunset is a general event that's fairly predictable. Think of your lifetime. Every day, you know the sun sets. Next day, evening time, sun sets. Next day, evening time, sun sets. Pretty soon you can predict that, you know what I think is going to happen tonight? The sun's going to set. The seasons. Right? Again, think of your lifetime. Think of the area that you live in. It's a general event that's fairly predictable. The leaves turn color, it's fall, you know pretty soon winter's coming. Winter lasts for a little while, then you know spring is coming. Once spring comes, you know summer is on its way. Then it's back to fall. Individual occurrences are much more difficult to precisely predict. Right? Like lightning storms, thunderstorms. Actually, often things with the weather are much more difficult to predict because they are an individual occurrence. A specific tornado. It's much harder to say, oh, there's going to be a tornado occurring at this time. Right? It's not like a sunset that you can say, oh, the sunset's going to occur at that particular time. Tornadoes, lightning storms, things with the weather, much more difficult to predict. It is much easier to make a prediction when you have lots of observations and there are few variables involved in the change. Next, we have state of equilibrium. State of equilibrium is a tendency to remain unchanged. Equilibrium means balance. So you get a couple kids on teeter-totter, seesaw. If they are balanced, they're remaining unchanged, then they are in a state of equilibrium. Dynamic equilibrium is what I call an oxymoron. If you know words that are oxymorons, like jumbo shrimp. Two words that mean kind of the opposite thing. Like jumbo shrimp, what is it? Is it small? Is it big? Is it jumbo or is it shrimpy? What do you mean? Well, dynamic equilibrium is like that. Dynamic means constantly changing, always changing. And we just said equilibrium is a state of balance, where it's not changing, it's staying the same. It's those kids balanced on the teeter-totter. So what's dynamic equilibrium? Is it changing or is it unchanging? Well, it's kind of both. Look at the picture. You got water going into this container. You got water going out of the container. So it's dynamic. The water in the container is constantly changing. It's flowing through that container. But if the rate of water going in to the container is equal to the amount of water coming out, what happens to the water level in that container? If you guessed it stays the same, you're right. It's in a state of dynamic equilibrium. So the definition for dynamic equilibrium is when we have a balance between two opposing processes. Water going in, water going out. A balance between two opposing processes that are going at the same rate in a system. So if the water going into that container is equal to the amount of water going out, then we have a balance. Two opposite processes, dynamic equilibrium. You can think of dynamic equilibrium in an environment with a body of water, right? A lake, a pond. If the amount of water going into that pond from precipitation, rain, if that is equal to the amount of water leaving the pond, evaporation, then what's going to happen to the level of water in the pond? It will stay the same. That's dynamic equilibrium. Right? Having grown up near the St. Lawrence River and Lake Ontario, you probably know there are times where maybe the lake or the river is in dynamic equilibrium. Maybe the water level does stay the same for a few days or a week. But we also know that it doesn't always stay the same. It's constantly changing. So there are times where our bodies of water are not in dynamic equilibrium. Streams can be in dynamic equilibrium. We'll learn about the words erosion and deposition. Erosion is where the stream is carrying stuff away, carrying sand and rock pieces away. That's when the water goes fast, like this picture. The water's going really fast, they have a lot of erosion. Well, where the water goes slow, it drops the stuff off. That's deposition. They're kind of two opposite processes, taking stuff away, dropping it off. Well, in streams, you can find places that are in the middle, that the water's not going really fast, the water's not really going slow, and you have a dynamic equilibrium. It's carrying away as much stuff as it is dropping. That's a case of dynamic equilibrium. And for our last video, I'll show you dynamic equilibrium on a moving walkway. I don't know if you've ever seen a moving walkway. It's a video of my daughter at the airport. And a walkway is like an escalator, but it's flat. And it just goes flat, and you can get places faster in the airport by going on them. I want you to watch the video of her because she can walk with the walkway or can she walk against the walkway. And there is a point where she will go against it and get in dynamic equilibrium. The point when she's walking backwards while the machine is going forwards, and the rate that she goes backwards is equal to the machine going forwards, you will finally see her stay still. Or it looks like she stays still. Dynamic equilibrium. Okay, we have the moving walkway at the airport. It's bringing the person forward. Now turn back. Reverse direction. Walk faster. So she's going backwards on the forward. All right, now show me equilibrium. Maintain equilibrium. Good.